So the next presentation is recorded. The presenter is Sihui Li from Zhejiang University in China. And then the questions will be fielded by Dr. Dan Wu, who's welcome to come up here after. Thank you. So
Hello everyone, I'm Sihui Li from Zhejiang University. It's truly a great pity that I cannot be there with you in person today for this talk. I sincerely hope that this pre-recorded one can still effectively convey the key information and insights of our work. Thank you for tuning in. Today, I'd like to share our recent work where we used post-mortem human brains to investigate how microstructural biases affect the assessment of perivascular flow. Our goal was to revisit the ALPS index, a biomarker used to assess glymphatic activity in the brain. I have nothing to disclose. So what exactly is the ALPS index? ALPS stands for Analysis Along the Perivascular Space Using Diffusion Tensor Imaging. It was designed to review global glymphatic activity by calculating the ratio of diffusivity along the x-axis to the diffusivity in other directions within specific fiber areas. However, recent studies have suggested that this ratio might be influenced by the microstructure of brain fibers. That raises an important question. Does the decrease in the ALPS index truly indicate glymphatic dysfunction, or is it simply a reflection of microstructural changes? To delve deeper into this issue, it's worth noting that a previous in vivo study reported that in widespread white matter region, the diffusion tensor showed that the second entry value lambda 2 was about 50% higher than lambda 3, even in the region without the perivascular space. It was called a radial asymmetry, which is due to the white matter microstructure. However, it is difficult to separate the microstructural effects from the lymphatic flow directly in vivo MRI. In our study, we turned to the post-mortem brains. Previously, we obtained diffusion-weighted imaging with a high p-value on 18 post-mortem brains. 9 were amyloid beta positive and 9 were negative. By measuring the microstructure effect for the ground truth, we aim to address these issues. The first is the microstructural effects related to Alzheimer's disease pathology and aging. And second, can we correct the ALPS index to minimize these microstructural effects? And finally, how does the corrected ALPS perform when applied to in vivo data? Our hypothesis was that in post-mortem scans, the vessel has collapsed, which means that any measurement of the ALPS index would solely reflect microstructural components without the influence of perivascular flow. Let's think about it with the diffusion tensor model. In the association fiber area, for example, the ratio of diffusivity along the x-axis dx to the z-axis, which is dz in vivo, is influenced by both perivascular flow and microstructural effects. However, in post-mortem data, since there is no flow, the ratio represents only microstructural effects, which we refer to as asymmetry in our study. In the calculation of ALPS index, we consider the two parts of asymmetries, projection asymmetry and association asymmetry. We proposed a corrected ALPS formula where these asymmetries are accounted for by multiplying them into the denominator. Under the post-mortem condition, the corrected ratio should equal to 1. For in vivo cases, since the actual asymmetries are unknown, we estimated correction factors alpha and beta based on the individual's age or A beta status. We measured the symmetries in the 18 post-mortem brain diffusion tensor imaging and found that projection asymmetry was dependent on A beta pathology, while association asymmetry was negatively related to age. This finding suggests that the pure macrostructural asymmetry is not only evident, but also dependent on pathology status and aging. As a result, in the corrected ALPS, we estimated the correction factor alpha based on group differences in A beta status, and the correction factor beta was calculated using linear regression between association asymmetry and age. We further validated the corrected ALPS in the in vivo data. Briefly, contrary to the original ALPS index, our corrected index did not show significant differences between normal individuals and those with clinical or pathological signs of Alzheimer's disease. It also showed weaker correlations with clinical assessment in the ADNI dataset. In summary, our research reveals that white matter microstructural asymmetry in post-mortem human brain ALPS varies on A beta pathology and aging. And by using these post-mortem findings to develop a corrected ALPS index that minimizes microstructural bias, we observed a reduced correlation between in vivo ALPS indices and AD markers. This collectively suggests that microstructural symmetry itself can serve as a valuable biomarker for Alzheimer's disease, offering a distinct measure that should not be misinterpreted as solely reflecting lymphatic function. To conclude, I'd like to share an update on this work. The full paper is currently under peer review, so if you are interested in delving deeper, please feel free to scan this QR code on the screen to access our preprint version. Finally, I'd like to express my gratitude for those collaborative efforts that made this research possible. We are in debt to the ADNI database for the in vivo MRI dataset. The post-mortem brain donors, they were registered with the National Human Brain Bank for Health and Disease at Zhejiang University School of Medicine. And our team was responsible for acquiring a portion of the hemisphere post-mortem MRI data, some of which has been previously reported and published. The partial data is publicly available now. Thank you for your attention, and I'm happy to answer any questions you might have.
Okay, we'll thank our virtual speaker. So this talk is now open for questions. We have a bit of extra time, so anyone from the audience, and Dr. Wu, if you want to stand up at the mic. In the meantime, I have a question. It's regarding the high b-value that was used. So what is your thought on the choice of b-value? Because typically lower b-values, like 1,000, would be used. How does that influence the findings?
Thank you. Happy to answer the question. So in the ex vivo sample, actually, the ADC is kind of twice or triple the times lower than the in vivo sample. So for example, if you want to do like p-value 1,000 or 2,000 in the in vivo sample, then you have to like double or triple that p-value in the ex vivo sample. So we make it like 6,000 p-value for the ex vivo acquisition.
Okay. And a follow-up question is, what do you think is in the ex vivo brain? Obviously, there is no blood flow, but what is the contribution of crossing fibers?
Well, our assumption is that the crossing fiber remain the same as the in vivo observation. So, yeah, the idea is that because there's no lymphatic flow in the ex vivo sample, so we can get a pure microstructure effect on the ALPS index. So yeah, this asymmetry indeed comes from the crossing fiber. So that definitely is in the ALPS region. So we find this effect of microstructure asymmetry due to AD status and due to aging. So we think what reflected in the ALPS index is coming from both the microstructure effect and lymphatic effect. If we want to like make some conclusion about lymphatic system, we have to exclude the contribution of the microstructure.
Okay.
Yeah.
Any other questions? Okay, if not, thank you.
Thank you.
For answering the questions.